Hello viewers, Wagdaru now taking you through the story of A-level physics paper 2. And this video I'm going to go through the topic under capacitors, and that part we're going to cover will be arrangement of capacitors in circuits. So this video is suitable for students in both Senior 5 and Senior 6 offering physics as part of their combination. So before we proceed, let's first look at the course outline for this physics paper 2. Now, physics paper 2 is divided into 4 parts. The first part is geometrical optics, where 2 questions come from these topics and the students must answer 1. That is compulsory. Then the next part is physical optics, or what we call waves. Also 2 questions come from these topics and the student must answer 1. The third part is electrostatics and electricity, where 3 questions come from these topics. And the fourth part is magnetism and alternating current, where 3 questions come from these topics. So here it is up to you. You can choose to answer 2 from here and 1 from here to make the 5 questions. Or you answer 1 from here and 2 from here to make the 5 questions still. So any option is okay. Now in the previous videos, we have covered the first part is already covered, this part is already covered, and this one is already covered. So in this video, we are going to go to part 4, which is arrangement of capacitors in circuits. So you're interested in calculations, but full notes are available in the book called Mastering A-Level Physics Paper 2, where worked examples, clear notes, worked examples, and try questions are available in all these topics. So if you need a copy, you can contact the author on these numbers. But in this video, you shall be interested in the worked examples found in this book. So we shall start our topic, arrangement of capacitors in circuits. So there are 2 types of arrangement of capacitors in circuits, and that will be series arrangement and parallel arrangement. So capacitors can be arranged in series or in parallel. We shall see what each means. So let's start with series arrangement of capacitors. So what we are going to do, we are going to first derive a formula which can be used to get the capacity, to get the effective capacitance of capacitors arranged in series. So we shall consider 3 capacitors, 3 capacitances C1, C2, and C3 connected in series across a battery as shown below. So we shall need an illustration. So those are the capacitors. Now, because of this PD, there will be charge on each of these capacitors and also a PD for each. So this PD V1 is the one across this capacitor, V2 is the one across this capacitor, and V3 is the one across this capacitor. Then because of the polarity of this dry cell or battery, this is a positive negative polarity, meaning that this part will be positively charged and this one will be negatively charged. Positively charged, negatively charged. Positively charged, negatively charged. So what you should realize is that all the capacitors have the same magnitude of charge. That is 1. Then 2, you realize that the PD across each capacitor is different. For this one is V1, for this one is V2, and for this one is V3. So whenever 2 capacitors are in series, just know charge will be the same and PD will be different. So as I've told you, capacitors in series have the same charge. And total PD, because PD is different, total PD will be the sum of all the individual PDs. Therefore, total PDV is equal to V1 plus V2 plus V3. But we know that V is equal to Q over C. We have already seen this formula. V1 is equal to Q over C, C1. V2 will be Q over C2, and V3 will be Q over C3. So it should have been Q3, but because the charge is the same, that's why you put the same letter, Q throughout. If it was different, we would have used Q1 here, we would have used Q2 here, and we would have used Q3 here. But because it's the same, we shall use the same figure, the same symbol. Then from there, what I'm going to do, I'll substitute for V1, V2, and V3. Then I'll realize that Q is common. I can factorize it out to remain with 1 over C1, 1 over C2, and 1 over C3. Then from there, I'm going to bring this Q this side to come up with Q over V. Therefore, I'll come and say that if C is the effective capacitance of the system, it implies that C is equal to Q over V. But we already have here V over Q, meaning that if Q over V is C, then V over Q will be the reciprocal, which is 1 over C. So this is what we use to get the effective capacitance of capacitors in series, in case there are 3 or more. But if there are 2, there is a special, it will be regarded as a special case. So in summary, when capacitors are connected in series, one charge on each capacitor is the same, and total charge is equal to the charge on any one of the individual capacitors. This is just a summary. Then the effective capacitance is less than the least individual capacitance. So the effective one, or the total, must be less than the smallest of those capacitors in series. Then 3 is that PD across capacitors is inversely proportional to their capacitances. We have already seen that V is Q over C, meaning that they are inversely proportional. Then total PD is the sum of the individual PDs. So that is the summary. Then, like I told you, there's a special case if there are 2 capacitors in series. So if 2 capacitors of capacitances C1 and C2 are connected in series across a battery, the effective capacitance C of the system can be got as follows. So still we use the same formula. 1 over C is equal to 1 over C1 plus 1 over C2. And when we get the LCM of this, it will be C1, C2. Now C1, C2 divided by C1, you get C2 times 1 to give you this C2. Then C1, C2 divided by C2, you get C1 times 1 to get C1, which is this. Then from there, when I get the reciprocal, here it will be C over 1, and here it will be product over sum. So this is the way we can get capacitance of 2 capacitors in series. The numerator will be a product, and the denominator will be a sum. Now that was series. Now what about parallel arrangement? So still we need to derive a formula which can be used to get the capacitance of capacitors connected in parallel. So consider 3 capacitors or capacitances C1, C2, and C3 connected in parallel across a battery as shown below. So we need an illustration. So those are the capacitances in parallel, and this is the PD across them. So in this case, you realize that the charge is different on each capacitance, on each capacitor. So here the charge divides. So here the charge is true at this point, but when it reaches here, it has to split. One is this, goes this side, another on this side, another on this side. So this will be the motion of direction of current, and this will be the direction of charge. So the charge will move in this direction, and when it reaches here, it will split, one this side, one this side, and one this side. So that is why we see here Q1, Q2, and Q3. So that is what you should remember. Under series, the charge was the same, but when it comes to parallel, the charge will be different. 2, under series, the PD was different, but when it comes to parallel, PD will be the same. So here you should come as that PD across each capacitance in parallel is the same, but the charges on each capacitor are different. Therefore, total charge is given by adding all the three. So Q is equal to Q1 plus Q2 plus Q3. But we know that Q is equal to CV, therefore Q1 is equal to C1 plus Q1 times V, Q2 is equal to C2 times V, and Q3 is equal to C3 times V. Therefore, I'll come and substitute for Q1, Q2, and Q3. Here I realize that V is common, so I'll pull it out and divide throughout by V to come up with Q over V equal to C1 plus C2 plus C3. Then if C is the effective capacitance, effective means total, it implies that C is equal to Q over V. And when I substitute this Q over V, I'll come and replace it with C to come up with C equal to C1 plus C2 plus C3. So what does that mean? It means that when capacitors are in series, the effective capacitance is got by adding all the three, all the capacitors. But when they're in parallel, it is different. For example, if there are two capacitors in series, it will be got by product over sum. But if there are more than two, you have to use the reciprocal, as we have already seen. So shall I make a summary that if capacitors are connected in parallel, it implies that the PD applied across each capacitor, PD is applied across each capacitor, and it will be the same. Then the total charge is equal to the sum of the individual charges. Then the effective capacitance is the sum of the individual capacitances. So those two formulae of series and parallel, we can go through these questions. So question 1 came from UNEB 2014 paper 2 question 10D and says a capacitor X of 5 microfarad and another capacitor Y of 8 microfarad are connected in series with a 20-volt supply. Calculate Roman 1 the charge on X and Roman 2 the potential drop across X. So here I shall need to make a simple sketch to illustrate the question. So you have this capacitance X and this capacitor Y with capacitance 8 microfarad. And this is the PD applied. So they are connected in series. So one should say that total capacitance is equal to, because there are two capacitors in series, the effective will be got by product over sum. So product of these two is here, and sum of these two will be denominator. When we use the calculator, we shall come up with this, and the unit is microfarad because these ones were in microfarad. Then total charge, remember when they're in series, the charge is the same, therefore total charge will be equal to total capacitance multiplied by the total PD, which is this, to give you this as the total charge they wanted. Therefore, because the charge is the same, it implies that the charge on X will be this. So if they had asked for charge on Y, we would also get this same value. So now shall go to Roman 2. Roman 2, they want the potential drop across X. In other words, the PD across X. So PD, the good thing, we know the charge on this capacitor and also we know its capacitance. Therefore, we can easily get the PD by saying Vx is equal to Q over Cx. So the charge is Q and the capacitance is Cx. That's why you are using Q over Cx. So our Q is this and our capacitance is this, but we have to convert to farad. Then in the end we shall come up with this as the PD they wanted. So that was question 1. Now we shall go to question 2, which came from UNEB 2010 paper 2 question 10C, and says 3 capacitors of capacitances, these ones, are connected as shown in figure above. Calculate the energy stored in the 2 microfarad capacitor when fully charged. So this is the circuit they are giving us, and previously we had already looked at the formula for energy stored in a capacitor. So shall use that formula to come up with a solution for this question. So first is to get the effective capacitance. So we are going to combine capacitors 0.7 and 0.3 in parallel. So I think we realize that these ones are in parallel because if charge flows up to here, it has to divide one this side and one this side. Now because charge is different, it implies that these two are in parallel. So you are going to first combine them to get one capacitance in parallel. So when I combine, because they're in parallel, you shall just add. So this plus this to give you 1 microfarad. So after combining, the circuit will become like this. So here there were 2, but now it is 1 capacitance. Then in that circuit, you realize that now these ones are in series because the charge which reaches here is the same charge which reaches there. So they are in series. And because there are 2 capacitances in series, we shall use the special case of product over sum. Therefore, combining this and this in series, capacitance will be product over sum to give you this microfarad. Therefore, total charge on C2. Now, in this case, it implies that we have got the charge on C2, which is the total capacitance, and we also know the total PD, meaning we can get the total charge. So total charge is equal to total capacitance times total PD, which is this, to give you that as the charge. And that total charge is the charge on each capacitor because they are in series. Therefore, energy stored in the 2 microfarad capacitor. So when you look at this 2 microfarad, capacitor, we have got the charge at this, and also we know this capacitance, meaning we can get the energy stored. So the charge with the formula is Q squared over 2C. I believe you already know this formula. So Q is this and C is this, which is here, but you convert to farad. In the end, you come up with this as the charge, as the energy they wanted. So that was question 2. Now we shall go to question 3, which came from UNEB 2016 paper 2 question 10B, and says a network of capacitors of capacitances, these ones, is connected to a battery of 9 volt as shown in figure below. So this is the circuit. Calculate Roman 1 the charge stored on the 50 microfarad capacitor. So the charge stored on this. And Roman 2 the energy stored in the 40 microfarad capacitor. So they want this charge. So this, because of this polarity, charge flows in this direction, and when it reaches here, it will have to divide one this side and one this side. What does that mean? It means that these two capacitors, this and this, are in parallel. So let's first combine those two capacitors in parallel. So when you combine this and this in parallel, it will we shall just add to give you 120 microfarad. So when we combine, the circuit will now become this. We have combined these ones into one capacitance. Now, after combining, you realize that because of this polarity, the same charge here will be the same charge at this capacitor. Therefore, these two capacitances are in series. Because they are in series and they are 2, we shall use the special case, which is product over sum. So the capacitance will be product over sum to give you 30 microfarad. So we now know the total capacitance and we know the total PD, meaning we can get the total charge. So total charge will be total capacitance times total PD, substitute. Now this was in microfarad, that's why we convert to farad by multiplying by 10 power negative 6. And then we shall get the charge in coulomb. After getting the total charge, we shall go back to the question. The question wants the charge stored on the 50 microfarad. So they want this, the charge at this point. Now the good thing, we already know we know the capacitance, but we don't know the PD. And we also don't know the charge which they want. Therefore, we have to first get the PD across this capacitance. So the PD across the parallel combination, so the PD across the 50 microfarad is the same PD across this because they are in parallel. So PD across that, we shall come and say it will be total charge over the capacitance for the parallel combination, which we got here, to give you the PD across the parallel combination as that. So now that means that the PD across this is 2.25, also the PD across this is 2.25. So now that we have got the PD here and also the capacitance, we can get the charge. Therefore, charge on the 50 microfarad will be C times V. So C will be the capacitance, which is this, and V will be the PD across that capacitance, which is that. So you come and substitute and get the answer they wanted. So now shall go to Roman 2. So Roman 2, they want the energy stored in the 40 microfarad capacitor. So 40 microfarad, we know this will be the capacitance, and we also know the total charge. That will be the charge across that capacitance. Therefore, now that we know the capacitance and the charge, we can easily get the energy stored. So you come and say that energy stored is given by that formula. Therefore, you shall substitute for Q, which is the total charge, and we got it here. Then the capacitance, which is the 40 microfarad, we convert to farad. And use the calculator, we shall come up with this as the energy stored. And that's what they wanted. So that was question 3. Now we shall go to question 4, which came from UNEB 2015 paper 2 question 9D, and says a 3 microfarad capacitor is connected in series with a 6 microfarad capacitor. The combination is then connected in parallel with 1 microfarad capacitor to a 12-volt battery as shown below. Calculate Roman 1, the charge stored by each capacitor, and Roman 2, the energy stored in the 6 microfarad capacitor when fully charged. So here they have helped us by specifying which ones are in series. So they have told us these are in series, and after that the combination is in parallel with this. So parallel, what does it mean? It means that parallel PD is the same. So the PD across this is 12 volt, and the PD across this combination is also 12 volt. So for this 1 microfarad, we have the capacitance and the PD, meaning you can get the charge straight away. So let's first do that. So you come out that the charge on 1 microfarad is equal to the capacitance, which is 1 microfarad, and the PD across that 1 microfarad, which is 12, to give you this as the charge. For these other two, we have to first combine them. So when I combine these one series, I'll use the method of product over sum to give you 2 microfarad. So when I combine the two, I'm going to come up with this. So that means that now these two are in parallel, meaning this PD across this we already seen it is 12, and also PD across C1 is also 12. Therefore, now that I know the PD across this C1 and also the capacitance C1, I can get the charge at this combination, series combination. So the charge on the series combination will be C1 times V, which gives you 2.4 exponent -5 coulomb. That means that because they're in series, they have the same charge. Therefore, the charge on each of this and this will be this 2.4 exponent -5. That is Roman 1. What about Roman 2? Roman 2, they want the energy stored in the 6 microfarad capacitor when fully charged. So they want this. So the good thing, we know the capacitance and also the charge. So you come as that energy stored will be Q squared over 2C. So the charge is that and the capacitance is that. You come up with this as the energy stored. So that was question 4. Now we shall go to question 5. Question 5 came from UNEB of November 1998, paper 2, question 10C. This is the circuit, and it said the figure above shows a network of capacitors connected to a DC supply of 120 volt, which is this. Calculate Roman 1, the charge on the 4 microfarad capacitor, and Roman 2, the energy stored in the 1 microfarad capacitor. So they want the charge on this. First of all, if this charge, the charge from here goes through this, and when it reaches here, it has to divide into 2. Meaning, to get this charge, we need to get the PD across this capacitor. And from there, it goes up to this. So the first thing to do is to combine these two capacitors in parallel. So combining 1 microfarad and 4 microfarad in parallel, I'll come up with this. I have to add the 2 to give you this. So when that happens, the circuit will now become this. So all these three are in series. Therefore, I have to get the effective capacitance in series. Because they are 3 and not 2, we shall use the reciprocal. So combining all those ones in series, we shall use the reciprocal. 1 over C2 is equal to 1 over 5 plus 1 over 2 plus 1 over 2. Therefore, when I use the calculator, this one will give me 6 over 5. Therefore, C2 will be this. So that C2 is the total capacitance. Now that I have the total capacitance, and also the total PD, I can get the total charge. So total charge will be total capacitance times total PD to give you this. And now that I know the total charge, it implies that I can get the total, I can get the PD across the parallel combination, because if you look at this parallel combination, the charge through across this, the charge through this will be the total charge, because the one which comes from here goes through here, goes through there, and also goes through there. So the charge of at this part is the total charge, and I also know the total and I also know the capacitance for parallel. Therefore, I can easily get the PD across the parallel combination, and it will be this. So now that I've got the PD, if I go back here, I now know the PD across this, and I also know the capacitance, meaning I can get the charge at that 4 microfarad. Therefore, the charge on the 4 microfarad will be the capacitance, which is 4 microfarad, and the PD, which is this, to give you this as the charge. So that was Roman 1. What about Roman 2? So Roman 2, they want the energy stored in the 1 microfarad capacitor, energy stored in this. So the good thing, I know the PD and I also know the capacitance. Therefore, energy stored will be a half CV squared. So come and substitute for C and for V to give you that as the energy stored. Then question 6 came from UNEB 2018 paper 2 question 10D and says a battery of EMF 120 volt is connected to a network of capacitors as shown in figure 6. So this is the circuit. Calculate Roman 1 the charge on C1 and Roman 2 the energy stored in C5. So in this case, charge will flow from here, goes here, it will split this side and this side. So the one here will come up to here and here, then the one this side will come here and split again, this side and this side. Here it will combine to go through this, and after that it will combine to go back to through C1 and back to the source. So what does that mean? So in order to get the effective capacitance, you have to first get where it last divided. So it is this part. So these two, we are going to first get the capacitance of these two combined parallel capacitors. So let's do that. So we shall come and say that combining C3 and C4 in parallel, we shall come up with that. So parallel we just add. Now when we get this, now the circuit will look in this way, because we have combined the two capacitances which were in parallel at this part. So that means that now next is to combine these two. Why are we combining the two? Because remember this charge last divided here, and from here this went through this to come here at this junction, and this one went through these two to come back at this junction. So that means that we have to first combine these two, which will be in parallel with this. So when I combine C2 and C6 in series, I'll come up with this. So combining those in series I have to use product over sum to give you 2 microfarad. So when I combine the two, now the outcome will now be this. Remember, here there are two capacitances, but now we have combined them into one. Now that you have combined them into one, you realize that this and this are in parallel, because at this point charge will divide or split. Therefore, the next thing to do is to combine these two which are in parallel. So let's do that. So parallel, just add to give you 3 microfarad. Now when they combine those two in parallel, the circuit will now become this. I think we realize that it is now simpler. So these diagrams are a side work. That is why they are not part of the main content. And that means that you don't need to draw them if you can easily internalize them in the head. So now these are the two remaining capacitances in series. Therefore, you can combine the two using product over sum to get the total capacitance. So when I combine, I'll come up with this product over sum, which gives you 2 microfarad. So now that I know the total capacitance and the total charge, and the total PD, I can get the total charge, and that total charge will be the charge on C1. If you look at this, the total charge you are going to get will go through this and this, so it will be the same charge on C1. So charge on C1 will be total charge and total PD and total capacitance. Total capacitance is this, and total PD, you already know it. It is 120, so it gives you this as a charge on C1. So that was Roman 1. What about Roman 2? For Roman 2, they want the energy stored in C5. Energy stored in this C5. So I know the capacitance, but I don't know the charge, and I also don't know the PD. So I have to get one of those. So the PD across C1, if you look at this, the PD across C1 will be equal to the charge over the capacitance, because I already know the charge, which is this, and I know the capacitance across the capacitance of C1. I can get the PD across C1, which is 40 volt. So now that I know the PD across C1, I can easily get the PD across C8 by subtraction. So PD across C8, now here they've called this PD across C5. Why? Because if you look at this, the whole of this and this are in parallel, meaning the PD will be the same, and the whole of all these ones is what we call the C8. If you are following, the whole of that is C8. So PD across C8 is the same PD across C5, because they are in, these two branches are in parallel, and the effective capacitance in parallel was C8. So PD across C5 will be good by subtraction to give you 80 volt. So now that I know the PD, I can easily get the energy stored in C5. I have CV squared to give you this as the answer they wanted. So now we shall go to question 7, which came from UNEB 2008, paper 2, question 10C, and says, the figure above shows a network of capacitors connected to a 10 volt battery. Calculate the total energy stored in the network. So total energy stored means you have to first get the total capacitance. So the capacitors are many, but it will not be that hard, because charge flows from here. When it reaches here, it splits. One goes this side and one goes this side. The one which goes here splits again. One goes this side and one goes this side. Then it combines to come here. Similarly, the one which went here splits. One goes this side and one goes this side. Then the one which goes this side passes through this to reach here, and also this passes through this to reach here. This junction, they combine to come through this, and at this junction they combine with this one to come through this, then they go back to the source. Now what does that mean? It means that these two are in parallel, then these two are in series. Then when you combine this in series and this one, these two will be in parallel. Okay, so it may be complicated if we combine all those ones, but what we are going to do, we are going to be breaking it down as we have been doing in the previous questions. So let's start by combining the 8 microfarad capacitors which are in series. So remember we said these ones are in series. So we are going to combine them into one. So series, it will be product over sum to give you 4 microfarads. So what does that mean? It means that now these which were 2 have now been reduced into one capacitance, which is 4 microfarad. Then we are going to combine C1 and the 2 microfarad which are in parallel. Now here, if you look at this and this are in parallel. So what we are going to do, we are going to combine them into one. So when you combine, you shall come up with 6 microfarad. And after combining, this is what will happen. So if you look at this previously, these were 2, but now we are combining them into 1 to give you this C2. After that, we are going to combine now C2 and the 4 microfarad in series. So this is C2 and this. So here we have this and this which are in series. When you combine them, we shall come up with C3, which is, so series, which is product over sum to give you 2.4 microfarad. So when I combine those two, it means I'll come up with a capacitance which is now 1. There were 2, these ones, but now we have combined them to give you one capacitance, which is that. Okay. So next we are going to combine the 6 microfarad capacitances in parallel. So we are going to combine these ones, these two which are in parallel. When you combine, you shall add them to come up with 12 microfarad. So that means that now these two have been combined in to give you one capacitance, which is this. Then from there you will realize that these two are also in series. Therefore, we are going to combine the two which are in series by product over sum to give you 2.4 microfarad. So that means that the circuit now becomes this. So initially there were these two, now we have combined them into one to give you this. I think we'll see that the circuit is now going on reducing and reducing. It is no longer complicated. So now what we have this and this which are in parallel, because at this point the charge divides. So when they combine those in parallel, we shall just add to give you 4.8 microfarad. So that means that now these two have been combined into one to give you this. So now I think I'll say that is now simpler because these two are now in series, meaning you can get the total capacitance. So combining this and this in series, we can get the total capacitance as that. So now that we know the total capacitance and we know the total PD, we can get the total energy from a half CV squared, and to give you this, and that will be the energy they wanted. So that brings us to the end of this video. Thank you for watching, and be reminded the next video will be on joining two capacitors. So if you are not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp so that you can all benefit as a family.